Smart Tank is the advanced maintenance analytics and troubleshooting system, a way of using cyber tech to accelerate maintenance diagnostics.
Hello, I'm Master Sergeant Aaron Cordrock from APSOC A4 down in Herbert Field, and I'm here to leave maintenance better than I found it with the introduction of AMATS. Imagine a utopian future where your car can tell you when it breaks, wirelessly inform your mechanic of what's broken, and help them with repairs. Introducing the Soccer Van 3000. Alright, full disclosure, that van is not from the future, and it is not why I'm really here, but it does bring up a good point. That van can do all the things that I just mentioned, but do you want to know what can? Most modern military aircraft. Aircraft maintenance is traditionally reactive, which directly impacts aircraft availability. And reactive maintenance is expensive. In 2022 alone, APSOC spent $12.6 million just on maintenance labor for the C-130J. That's not counting parts or logistics. For perspective on that, we spent $37 million on just our engines. And keep in mind, that's one of our most reliable aircraft on the ground, not completing missions. My goal is to maximize aircraft availability with the introduction of AMATS, the Advanced Maintenance and Troubleshooting and Analytics System. With AMATS, we'll process previously uncaptured data that will allow us to troubleshoot systems down to the component level while generating user-friendly dashboards that we can use to get a more accurate fleet status. And finally, we want to revitalize predictive maintenance by harvesting 131 times more data to give our perspective of aircraft health into high fidelity. All of this will be accomplished by using existing cyber protection hardware that's been required to be put on our aircraft for the past 10 years. Did you know that as an electronic component nears its end of life, its communication across the data bus slows? The Soccer Van 3000 does, and with AMATS, we can too. How it works is simple. Our device scrapes data from the aircraft, which is then wirelessly sent down to maintenance for rapid post-flight data aggregation. That information is then sent up to the cloud, where it is processed and distributed out. With this information, we can, for the first time, deploy our healthiest aircraft based on more sophisticated data, eliminate supply surges by ordering incorrect parts to troubleshoot our systems, provide our leadership more data to make smarter decisions, and finally, give our maintainers far more information to better fix our aircraft. Now, judges, here's our ask. For phase one, we need $5.3 million. This will encompass our hardware and software development, the installation costs, as well as allocating a cyber management team. For phase two would be an additional $3.7 million. This will develop our machine learning algorithms, as well as our data storage solutions. This will get us onto our 8 test aircraft. Later, if we'd like to budget the remaining 59 tails, would be an additional $11 million. Now I know $11 million is a lot of money, but what we're saying here is we're paying twice the price for 7 times the impact. The larger this program gets, the better the data is, and the cheaper it is to expand out. Our test bird, the MC-130J, will benchmark the entire departmental maintenance complex. This applies to all aircraft, not just the shiny new ones. For your consideration and vote, please help AMATS revolutionize maintenance above all.
But it's like other predictive maintenance things that are in development or in use. How accurately do you think, and tell me how you've been able to estimate what the costs are and what you're going to be able to produce for those costs? Because it looks to me like you've got a fairly major undertaking here, and you may not have adequately costed it. Could you talk about that?
So our original cost we put up isn't full encompassing from what our best guesses are. But this is also a cyber initiative that we're basically attaching maintenance onto. So we've already got cyber money to pay for the hardware and some of the software development. So we're kind of putting a blanket statement on the cost, but working with A4 and A6, we're able to bridge this project into a bigger, more encompassing animal. So it is going to be expensive, but we're already tapping into these requirements that we need to fulfill. And as it builds out, we're trying to make sure we get our foundation good so we can already involve some pre-existing predictive maintenance sectors like PANDA, and we're working with AFRL to make sure we have the right people in the room so when we build this out the first time we get it right.
So you're confident that when you can scrape the data that you can actually do that, and then it's actually have the processing to use it and display it in a way which will allow you to do more improved, more efficient maintenance.
Yes, sir. So we already scraped data off the aircraft, but the difference is on a 6-hour flight of 400 megs to with this new device, we can get 6 gigs of data. So it allows us to see predictive fails. So we can see when the LRUs begin to slow down, or more importantly, from a maintainer perspective, we can see when those LRUs are breaking. Instead of it just saying programmer fails, now we can see all the different communications that said why the programmer failed. So instead of throwing that part out, we can get the appropriate part and fix it right the first time, and hopefully get that part ordered as that plane is landing.
Is the focus on better maintenance or cheaper maintenance?
Yes. Yes, sir. So our original perspective was to try to save maintenance time. Nothing's worse than being on the flight line for 10 plus hours, troubleshooting a system, and just not being able to figure it out because we can't see the information that that system is telling us. So the idea would be we will produce better maintenance by getting the correct hardware onto that aircraft the first time, and in doing so we'll save tons of time, tons of money, and then hopefully get our airmen more invested in the knowledge that surrounds how the system operates as well.
In your analysis, understand saving time and money, but how's it increase aircraft availability? Have you been able to kind of determine greater aircraft availability, and, to what magnitude?
Yes, sir. So our perspective on this is the worst thing you can hear when an aircraft comes back code 3 is if its avionics fail, and it's one of those weird ones we just can't fix quick. If we have to turn for the next mission coming up, or if we're downrange, having a good 4 to 6 hour troubleshooting time block just built into maintenance is already putting us so far behind on getting that aircraft ready for the mission tomorrow. So being able to get this data downloaded rapidly post-flight, so where our troubleshooting starts with giving us all the information we need, it's going to cut our time in half, because we can go out with the appropriate part that we know has failed because we have this updated information, replace it, and then we can begin our troubleshooting if that didn't fix it, really get deep into it. But this should basically click the easy button for maintenance for avionics.
How does this compare or complement existing technology that's out there that's being used by commercial aviation?
Yes, sir. So industry leaders such as Delta are the forerunners for predictive maintenance and CVN+. This will back up onto those, but predictive maintenance that is traditionally used in those fields is based off lagging indicators. We know that this part fails every so many hours, so we can predict it's going to fail at this time. With this information, we should be able to harvest and process using AI and machine learning of what a component looks like before it fails. So rather, instead of saying, well, we've got 5,000 hours left, we can say, we know this is going to fail in 50 hours. Let's order it so when it lands, when we have time, we can swap it and it's predicted, it's scheduled maintenance instead of reactive.
All right.